Good morning and welcome to this next lecture on sound and structural vibration. We've been looking at sound radiation from a panel set in a baffle, in a rigid baffle. Okay. And we have come to understand the cancellation effect. Now we will try to understand the same phenomenon in the frequency domain, that means the Fourier transform domain. And we'll do this for a one-dimensional case. That means there is an infinite baffle that comes from minus infinity up till x equal to 0, and there is a 1D panel that is vibrating, goes off to infinity, and it extends till x equal to a. Okay. So now let us say that the velocity, okay, is put a tilde, is given by v tilde p sine p pi x by a e to the power of j omega t, and this is between xa and x0, and it's 0 elsewhere. Okay. Now we look at this in the Fourier domain, or we call it the wave number domain. Okay, wave number domain. And the definition we choose is the forward transform fkx is integral minus infinity to infinity f of x e to the power minus j kxx dx. Okay. And the inverse f of x is given by 1 over twice pi integral minus infinity to infinity f of kx e to the power plus jkxx dkx. Okay. So now if we just take the spatial part of Vn, okay, if we just take the spatial part, and apply the wave number transform or Fourier transform, that means the Fourier transform is applied to v tilde p sine p pi x by a. Okay. E to the power j omega t is left out. By the way, as before, Vp is the amplitude which is held constant. Okay, it doesn't change with frequency, it's held constant, and this mode is being driven at this frequency, any particular frequency. Okay. So now if we apply the Fourier transform to this, we will get v tilde of kx is equal to v tilde p pi by a minus 1 to the power p e to the power of minus j k x a minus 1 divided by kx square minus p pi by a whole squared. So if we plot this, okay, so if we plot the magnitude of this, we plot the magnitude of this, we get plus p pi by a minus p pi by a. We get a peak here, then these bumps, we get a peak here, we get these bumps, okay. This is how this looks like, magnitude v tilde kx. Okay. Now let me tell you that this is only and purely related to v tilde p sine p pi x by a. It has nothing to do with omega. It has nothing to do with omega. The moment you have this shape in the spatial domain and you put it through a Fourier transform, this is what you will get. Okay. Now we would like to compute power. We'd like to compute an expression for power from the panel, from the 1D panel. Okay, and so we'll compute that using acoustic power. We mean acoustic power. We'll compute that using the normal velocity and the pressure on the panel. Okay, we'll compute it using these two expressions. So now let us see here, how does it look like? The power, space averaged power, which I'll time averaged power, is given by 1 over t integral 0 to t, then integral 0 to a, the pressure expression x y at 0 comma t into Vn of x comma t, dx dt, and let's assume a unit width perpendicular to the paper. Okay, so this is kind of power per unit width. Okay, now we know that the time can be removed, get 1/2 real part of integral 0 to a and we get P. I'll put a tilde over it, x comma y equal to 0 into V tilde n conjugate of x dx. Okay, so here we took the pressure and velocity to be real. So just to clarify, we took the real pressure. Okay, let me do this. We'll make this real of P tilde, okay, and we'll make this real of Vn tilde. That's better. Okay, so real part of P tilde, real part of Vn tilde. Okay, so that I can have P tilde x comma y comma t as some other P tilde star x comma y e to the power j omega t. Okay, and I can have V tilde n x comma t is some other V tilde n star of x e to the power j omega t. This e to the power j omega t is the thing that always messes up. Okay, so we start with this, we take the real parts and we multiply and we integrate over time. Okay, that is now equivalent to, okay, that's now equivalent to the one here. Okay, okay, it's equivalent to this. So let's say P tilde star, okay, Vn tilde star. Now I'll make conjugate as a bar over here. This is conjugate. Okay, so here the time is removed using the PV conjugate relation. Okay, now this time averaged power is equal to the 1/2, okay, which is already there, and for this and this I am going to bring in inverse Fourier transforms. Okay, so which means I get a 1 over twice pi and a 1 over twice pi, and the real part, okay, then integral 0 to a. Okay, now for this spatial pressure on the surface of the panel, I will introduce the Fourier transform, which is minus infinity to infinity the P tilde kx e to the power plus j kxx dkx. Similarly, for the velocity part, integral minus infinity to infinity V tilde kx dash, okay, conjugate. Okay, let me make it a conjugate by putting this line here, e to the power minus jkx dash x dkx dash. This minus again because it's conjugate, and a dx at the end. Now the P tilde kx and V tilde kx dash have come from a panel vibrating only between this okay, the form of b tilde kx and the corresponding p tilde kx comes up only because the panel vibrates between 0 and a. Okay, so these inverse Fourier transforms will lead to those pressures which correspond to a panel vibrating between 0 and a and no vibration outside. Therefore, I can safely change this limit to minus infinity to plus infinity. Okay, so what do I get? I get power per unit width of the panel 1 by 8 pi square, okay, the real part integral minus infinity to infinity, now 0 to a changed to minus infinity to infinity, then minus infinity to infinity. Here I am replacing, this is where the earlier definition is used, omega rho 0 by k square minus kx square to the power half v tilde of kx into integral minus infinity to infinity. Here v tilde kx dash conjugate, okay, e to the power of minus j kx dash x dkx dash into dx. Okay, I was forced to use this bar because I try to explain it using conjugates here or stars here. Okay, so now there are, okay, it should be dkx here, dkx here. There is a dkx and a dkx dash integral and a dx integral. Okay, so we have to do one of these first, and we'll do the x integral first. Okay, why? Because x occurs here. Okay, one more thing here, e to the power of j kxx, miss that out. Okay, so the x occurs only here and only here, nowhere else. Okay, so we'll do the x integral first. Okay, so let's see. So what is that we have to integrate first? Let us see. We have to integrate minus infinity to infinity e to the power of j kxx minus j kx dash x dx. We have to integrate this. Okay, so let's see now. First, the definition of a delta function, of a Dirac delta function. Okay, so if we have an integral minus infinity to infinity delta of kx minus kx dash e to the power plus j kx dash x. Okay, just by definition of delta and dkx, okay, just by the definition of delta, so this becomes equal to e to the power j k x dash x. Okay, this function is shifted and kx dash comes in here. Okay, this is just the definition of. Now what I do, I put in a 1 over twice pi integral minus infinity to infinity delta of kx minus kx dash e to the power j kx x dkx. Okay, this is now the inverse Fourier transform of this function. This is the inverse Fourier transform by definition earlier of this function. So that gives me, including the Dirac definition, this divided by 2 pi, which is this. Okay, so now if I look at the forward transform, right, the forward transform of this now should give me delta back. Okay, so the forward transform, which is minus infinity to infinity, okay, e to the power j k x dash x e to the power of minus j k x x into dx by twice pi should give me back my delta function kx minus kx dash. Okay, which means what? Which means my integral minus infinity to infinity e to the power j kx dash x e to the power minus j kx x dx will be equal to twice pi delta of kx minus kx dash. Okay, so this is what we wanted. Okay, so in the earlier integral, we had previous page here for this part of the integral we'll replace it by twice pi delta of kx minus kx dash, and we are left with two integrals, one on kx, one on kx dash, but this delta will force both of them to be together, so they will collapse to one integral. Okay, so they will collapse to one integral. That means all will be kx's. So what we'll have as a resultant is that we'll have this power time average power per unit width given by 1 over 8 pi square and the twice pi from the delta part and a real integral minus infinity to infinity plus or minus omega rho 0 by k square minus kx square to the power half. Now the magnitude of v tilde ax square dkx. Okay. Now with this expression we had said before that k square minus kx square, if k is greater than kx, then we have a real value, we'll take the positive real root. If k happens to be less than kx, we'll take the negative imaginary root. Okay, so as long as k is bigger, this expression is real. Okay, so this real will choose, okay, as long as k is bigger than kx. The moment kx exceeds k, it's imaginary and the real will not choose it. So kx cannot exceed k in this integral if it has to survive. So we will get, with change of limits, 1 over 4 pi, real is removed now, integral kx is bounded by k, okay, and we take the positive sign, omega rho 0 by square root of k square minus kx square, okay, and magnitude we tilde kx whole squared dkx. Okay, so if I have to bring in the picture that I drew earlier, we had vkx shown like this, all these little bumps and a peak at p pi by a. This is kx axis, and then again bumps here and p pi by a minus p pi by a, and this was magnitude of vkx. So now comes the omega. So far omega didn't come in the picture, okay. Now comes the omega, okay. So I can choose omega equal to omega 1, then that would give me k1, which is omega 1 by c, okay. So now omega 1 decides k1, so let's say k1 is here, happens to be here, k1, okay. So we now integrate based on omega, this k value gets decided, okay, that's the only way k value gets decided. So now k is equal to k1 and the range of integration is minus k1 to k1, okay. So at this frequency only this range of wave numbers need to be integrated and power is computed, okay. But suppose the same panel, same mode is vibrated at a higher frequency, another omega 2, which means the k2 now is omega 2 by c, okay. So if I draw the k2 line, k2 is here and minus k2 is here, then this becomes k2 and k2. Now I get more wave numbers within the range, so the power will increase. In the limit I could excite the same mode at a further higher frequency where k is such that it crosses this plus and minus p pi by a, and then I would get the maximum power possible radiated, okay. So let us now, just for churning our head, okay, look at two cases, okay, examples, okay, and example 1, okay. Example 1 has two different problems. Within example 1 there are two cases possible, okay. So one is a plate, okay, which carries a certain wavelength, is set in a baffle as before, Okay, it carries a wavelength lambda 1 given by twice A1 by P1. Okay, that's first case. Within that, okay, the next is a panel now which carries the same wavelength but it is longer. So let us say this one is A1 and this one is A2. So this is also lambda 1 actually, lambda 2 which is equal to lambda 1, but it is twice A2 by P2. The number of half cycles is different. Okay. So if you compute the V tilde kx for both these cases, okay, they look very similar. They look very similar. Okay. In the main lobe, where it is P pi by A, or P1 pi by A1 or P2 pi by A2, the shorter one may have wider picture. Okay, the shorter one has a wider picture. So same here, wider picture for shorter one and thinner picture for longer one. Okay, but otherwise below the picture for both looks very similar. Okay. So if I excite both the panels at certain omega equal to omega 1, okay, which leads to a K1, okay, and it is less than the these wave number values, that means below coincidence of that mode, then K1 line can be put here, K1, and this will be minus K1 line, and the integration limits will extend between minus K1 and K1. And for both panels, because this range looks similar, you will get the same power. Power is same for both panels. Power for both panels same. Okay. Now what about radiation efficiency? Radiation efficiency sigma, okay, one of the terms in the denominator is the area of the panel. Okay. So now numerator, the actual power from panels is same for both, but in one case area is bigger. So this case area is bigger, so it will have lower radiation efficiency. Okay. So we have run out of time. The second example I will take in the next class. Thank you.